Question number 6C. It says find yq of t, the position of the particle q at times t. So this is our vertical position, and from above we've been given that the position at t equals 1 is y equals 2. So now in general, we can say that the area under the velocity curve is our displacement. So in this case, the area under the VQ graph is the change in the y positioning, okay? So we're going to use this change and initial starting point to come up with the equation for y. So we've been given initially only the velocity function for y, and we need to come up with a position function for y. So if we want to do that, we're going to do this. So the position function y, okay, so we're going to, maybe I'll just do this in a different color here. The position function y is equal to our starting position is going to be at y equals 2. And then we're going to add our displacement, how the y changes as we change the area underneath the velocity curve. So it's going to be the area under the velocity curve. We're going to start at 1 because that's our initial position. X is 1, t is 1, y is 2. And then we're going to go to time t. Time t. Okay, and maybe I should really write this as a function. Yq as a function of t, and that's going to be the area under the VQ graph. Okay, so there's our equation, the yt function as for the position y as a function of time. Okay, and as we move along the x-axis here, as we increase our time, we're going to calculate the area underneath the velocity graph to figure out how far we've moved from that initial position of x equals or t equals 1, y equals 2. So there's our equation. For D, it says, as t goes to infinity, which particle will eventually be farther from the origin? And give reason for your answer. So essentially we want to know the position, x position and y position as t goes to infinity. Well, the x position, all we're going to do is we've been given the function 6 minus 4e to the negative t, and we just want to know what happens as t goes to infinity. So we're just going to take a limit here, and as we evaluate this limit, the limit as t goes to infinity of our x position, we end up with e to the negative infinity, which is 0. So we're going to end up with x equals 6 as t goes to infinity. So basically the x goes closer and closer to 6 units away from the origin as t goes to infinity. For the vertical position or y position, we're going to take that function that we calculated up here. This is going to give us the position of y, and we're just going to let t go to infinity. To do that, we really should have a limit. So I'm just going to, for the area part, as we calculate the area underneath that velocity curve, we're just going to use a limit because t is going to go to infinity, and we're just going to evaluate this limit. So when we evaluate this limit, this works out to be 2 plus, we're going to anti-differentiate the 1 over x function, so we get negative 1 over x, and then we're going to use, sorry, I need to use my limit notation still. This is going to be the limit as t goes to infinity of the antiderivative negative 1 over t, so 1 over x, and this is going to give us the bounds from 1 to t, and we're going to let t go to infinity. So this is 2 plus, and as I plug infinity into here, I'm going to end up with negative 1 over infinity, because t is going to be infinity, minus negative 1 over 1. Okay, so this works out to be 2 plus, that works out to be 0 plus 1. So the y position is going to be at 3. It's going to get closer and closer to 3, y equals 3, as t goes to infinity. So which particle will eventually be farther from the origin? Okay, the x particle will be further. Okay, because it's going to be 6 units from the origin, whereas the y particle will be 3 units from the origin.